All right, so let's do a little review of what the last video did was finding derivatives of composite graphs. And I guess I should say this is for the worksheet 14.6. Okay, so basically a little review here of doing directional derivatives. Okay, so if this is our function, f of x comma y comma z, and keep in mind that this could be represented by another letter like w of that. And let's say we're doing this at the point of 1, 2, 0. And then the direction that we're going is 2, 2, 1. Okay, so basically, so finding the partial derivatives of f of x, y, and z. Oops, and I guess that would help if I give you the function. And let's say the function is x squared plus y e to the z. Okay, so the gradient, so the derivative of x would be just 2x, comma, derivative of y would be e to the z, and derivative of z would be y e to the z. And then, of course, since I gave you the point, made it real simple there to start off with. The point is at 1, 2, 0, and that would be 2. Z would be 1, and y would be 2. Okay, so now the directional derivative. So I got to find the magnitude. So that would be the square root of 2 squared plus 2 squared plus 1 squared. So what's that? Square root of 4 plus 4 plus 1. So that would be square root of 9 or 3. Or in this case, the directional derivative du would be 1/3 of 2, 2, 1. So now multiplying the directional derivative times the gradient, I would have 2, 1, 2 dot 2, 2, 1, and I'm going to pull the 1/3 out there. So I have 1/3. So that would give me 4 plus 2 plus 2, 4, 8, and what we'd have would be 8/3. Okay. So just changing how I present the information. So let's say t instead of f, so x, y, and z. And let's say we have x squared plus y e to the z, same function again. But I give you that as c of t, and you would have t squared, excuse me, just go t cubed, t squared, and t would be at 2. Okay, so basically the point then can be found quickly that I'm going to plug into my function by finding c of 2. So therefore my point, and I guess I could write it with parentheses there, this should be 8, 4, 2 is now the point. So therefore find the gradient of t of x, y, z. So again, having the same thing here, I'll just redo it here. I have 2x, y, e, z, and then y, e, z. So now the point I'll be using would be 8, 4, 2. So in this case, it would be 16, e to the 2, 4 e to the 2. Now my directional derivative then be c prime of t, and therefore the derivative of this would be 3t squared, 2t, 1, and then for c time of 2, I would have 4, 12, 4, and 1. Now you got to find the magnitude. If we are doing the directional derivative, okay, we have to find the magnitude. If you're just doing the derivative, just multiply the two vectors together. So anyway, the magnitude would be 12 squared plus 4 squared plus 1 squared. So therefore, the magnitude I do believe is square root of 161. Therefore, the directional derivative would be 1 over square root of 161 of 12 for 1. And therefore, take the directional derivative, dot it with the gradient of t, and what I'd have is 16 e squared 4e squared, dot it with 12 for 1, and we have 1 over square root of 161. Okay. All right. Quick review. A little note here. If I just ask you to do, let's say, partial d dt of t of c of t, if I was asking just for that, not the directional derivative, but just the derivative t of c of t, a function composition, then basically it'd be the same thing. It would be this, take away the unit vector piece. So it'd be that piece only, like that for your final answer. Okay. All right, so what I'm going to do here is add a few more variables in and show you it follows the same pattern. So it doesn't matter how many I add, you just follow what we've been doing, kind of like a puzzle, and hopefully you'll see the pattern here. So let's start off with just a simple one here, and let's say have x, y, and let's say we have x of t and y equals y of t. Okay. Now keep in mind that this is the same thing as z. Therefore, if I ask you to find, let's say, partial dz of dt, or if I say find the derivative ddt of f of x of t, comma y of t, what you have then is taking the derivative of the function according to each individual variable, so the gradient. So you have the partial derivative of f according to dx, and then partial derivative of f according to dy, and then we're not doing the directional derivative, just doing the derivative. Therefore, this would be like your c of t, doing the derivative of dx, dt, and dy, dt. Okay. If I add an extra variable to this, okay, so let's say we have f of x comma y comma z. So again, they might use, let's say, w equals f to represent that. And then if my c of t, let's say if I do something like this, say g of r comma s, y equals h r of s, and then say z equals j of r comma s. Now you might think there's a lot of a lot of variables here, but really it's not. It's the same process. So if we go through and I ask you to say find the partial derivative w, and let's do it in terms of r first. That would be the same thing as, say, do a d dr of f of g of h of I. So what would that look for in terms of my dot product? Well, again, you got to take the function, this piece here, and that'd be partial df according to first x, and then the partial of f according to y, and then partial of f according to z. Okay. Now, what are you going to do the dot product of? Okay. Well, since we are doing it in terms of r, I'm going to do dx according to dr, then y according to dr, and dz according to dr. Okay. Now, let's put an OR statement, just going to change it up a little bit. So let's say I say partial dw of ds. Just notice there's r and s here. So that would be the same thing as d of ds of f of g, comma h, comma I. So it does not change this at all. You still changing that, taking that function, doing the partial derivatives of that, converting it into a vector. So df dx, df dy, df dz, but okay, my dot product, this would be dx, but now we're doing it in terms of s, not r. So this would be ds, dy according to ds, and dz according to ds, like so. Okay, and don't worry, I'm going to give you some examples here in a little bit. Okay, but I just wanted to kind of give you, show you a pattern of how it is not changing. Just got to watch out in terms of what you're doing the derivative of. Okay, notice this here, when you take the function, okay, you take the function and convert it into a vector, so you have to do it by partial derivatives. The only other part then is like the CFT, basically. All right, so let's use an example here. So let's say we have w of f of x comma y comma z, and let's say my function is x, y, plus z, and my x is s squared, my y is st, and my z is t squared. Okay, so I'm not giving you any numbers. I just want you to do this. I want you to find dw ds, which means that would be the same thing as saying the derivative ds of the function f of x comma y comma z. Okay. All right. So first thing, got to find the gradient. So let's do that. So taking your function f of x comma y comma z, and your gradient, so we're converted into a vector. So derivative of x is 1y, derivative of y would be 1x, and derivative of z would be 1. Okay? Okay, now the point that we are plugging in here. Okay, so here's my x, here's my y, here's my z. So the point that I'm plugging in here is s squared for my x value. For my y value, I'm plugging in s of t. And for my z value, I'm plugging in t squared. So what's my y value here? It is s of t. What is my x value? It's s squared. And obviously it's just a constant, is 1. All right, so we got our gradient, ready to multiply it by our c prime, basically. So let's come back and we got to do the derivative. But what are we doing the derivative of? We are doing the derivative of s. So dx ds. So what's the derivative of s? That's 2s. Okay, what is dy ds? Well, that'd be just 1t. And dz ds, well, there's no s there, so what's the derivative of constant? It is 0. So therefore, my vector would be 2s, comma, t, comma, 0. So now do the dot product. You have 2s squared t plus s squared t plus 0. And since those are the same, we can add those together. And there is our function, and then we can start throwing numbers in anytime we want. Okay. All right. Let's do another example here. All right. So let's say we have again z equals f of x comma y equals exy. And we'll represent this a little bit different. I'm going to say at s t u, and the point is 2, 3, negative 1. Okay, and I want to do this when x is st and my y is s minus ut squared. Okay, so notice the pattern stu for the pattern of like kind of x, y, and z. Okay, so I want you to find dz dt. Okay, so let's start off with our gradient. So our gradient of f of x comma y. So converting this into a vector. So the derivative of x would be exy. So the derivative of x would be just a y there. And then this would be exy. Okay. Now, what is my x? What do I plug into that? Well, here's my x. My x is s to t. So wherever I have an x, I'll put s to t in. For my y, I'm going to plug in s minus ut squared. Okay. And I guess I could probably make this a little bit simpler too. I should come back here and plug in my values, my numbers. So let's plug in 2 for s. So that's 2 times my t value, which is 3. So it looks like that's going to be 6. My s, again, coming back, is 2 minus my u is negative 1. And my t is 3 squared. So what is that? 2 plus 9. So it looks like 11. Okay, so coming back now. And I could have done that up earlier, but anyway. So what is my gradient now? Well, my y is 11. E, and multiply those two together, so that's 66. And this would be 6e66. Okay, there's my gradient. So now let's come back and do the derivative. Now, we are doing it in terms of t now. So dx according to t. So what's the derivative of t? That'd be 1s. Derivative dy or dt. And also that would be 0 minus 2ut. Okay. I just want to double check, make sure I did the derivative. All right. So plug in my values in now. And plug in my s is a 2. And this would be a negative 2. My u is negative 1. And my t is 3. So what does that give me? So come down here, dot it. I have 2 comma, looks like 6. All right, so now it's got the basic things to do now. Do the dot product. So we have 22e to 66 plus 36e to the 66. And it looks like we can add those together. So we have 58e to the 66 at that particular point. Hopefully you're starting to see a pattern here. All right, so let's do one more. And hopefully you can pick up on this. All right, so let's say z equals f of x comma y comma z is x to the fourth y plus y squared z cubed at, and let's say r s t at the point 2, 1, 0. Okay, now my x is going to be represented by r s e t. My y is represented by r s squared e to the negative t. And my z is represented by r squared sine of t. All right, so which one do we want to find here? Obviously dz, but which letter? So we have r, s, and t. So let's just do dr. Okay. All right, so let's start off with the gradient. So we're going to change. So we got to change this function into a vector. Okay. So the gradient of f of x comma y comma z. So first off, doing the derivative of x would be 4x cubed y. Oops, plus. And oops, that'd be 0. Looks like. Now the derivative of y. So it looks like x to the fourth plus 2yz cubed, comma. Now the derivative of z would be 3y squared z squared. Okay, now we want to plug a number in here as soon as possible. So notice, okay, where is my x? Let's come back here. So what is my x at that number? Okay, so r is 2, s is 1, and e to the 0 is 1. So x is going to be represented by 2. Now my y, plug in my r is 2, s squared is 1, and 1 again. So y, when you use 2. Z, r squared is 4, and sine of 0 is 0. So z is 0. So the point for my gradient, I'm going to use 2, 2, 0. So what I have here will be 4 times 8 times 2. Next one would be 16 plus 0. And 3 times 0. So therefore my gradient, I'm going to be using 864, comma 16, comma 0. All right, we got our gradient. Now, since I don't have a whole lot of room here, I'm going to box that in. Don't forget about it. Now we want to do the derivative according to r. So we want to do dx dr. So I'm looking up here. Okay, so what's the derivative of r only? That would be 1, and that would leave me with set. Now doing dy dr. So I'll come back up here. So derivative of r would be again just the 1 s squared e negative 2, and then dz dr. Okay, that would be 2r sine of t. Okay, so let's plug in our numbers here. Okay. So what we have, I gotta see, let me rewrite here, r s t is 210. Let me rewrite them there so I can see it, move things up now. So for this one, we have 1, s is 1 and 1, so that would be 1. For this one here, be 1, s is 1 squared and 1 again. So that would be 1. And for this one here, it'd be 2 times 2, and sine of 0 is 0, so that would be 0. So basically, like my c prime of t would be 1, 1, 0. Okay, so let's box those in. So here's my two values that I have to do a dot product on. So let's go ahead and do that. So we have my gradient 64, 16, 0, and dot it with 1, 1, 0. So I have 64 plus 16 plus 0, and looks like it is 80 would be the answer. So hopefully you're starting to see how the pattern, doesn't matter how many variables I throw in, it's the same thing. Just like a puzzle. Just start plugging in, find your gradient, get that piece plugged in, and then find your basically your c prime of t, plug the numbers in there, do the dot product, and you're done. All right. Hopefully that makes sense, and we are almost finished. Like I said, that's 14.6.